Topic 13. Vectors. Manipulations of vectors, or operations of plane vectors, as it may be known. Today, we will be adding and subtracting vectors and multiplying vectors by scalars. Key terms: scalar, a non-vector quantity with size but no direction, and resultant force, the combined effect when vectors are combined. Addition and subtraction. As with polynomials, they act similarly to normal numbers. So vector A add vector B, so when B is equal to A1, A2, and B is equal to B1, B2. Then A add B is equal to A1 add B1, A2 add B2. Vector A minus vector B, similar to addition, except instead of adding them, you minus them. So A minus B is equal to A1 minus B1 and A2 minus B2. Scalar multiplication. So if A is a vector, we define 2A is equal to A add A, and 3 is equal to A add A add A. So minus 3A is equal to 3 times minus A. So then it's minus A add minus A add minus A, which is handily shown in this graph. So you've got A is a vector here, so then A, and then another vector of A, minus A, minus A, minus A, because it's going downwards, whereas all these ones are going upwards. So if you're going to times the vector V by minus 1 here, this is important, you would times V1 by minus 1 and V2 by minus 1. So you'd have minus V1 and minus V2, which would be minus V. If you're going to multiply it by 0, you multiply V1 by 0 and V2 by 0. 0, 0 is equal to 0, which is, again, the 0 vector. And this is important because it means that whenever you're multiplying a length, you're multiplying each unit of the vector by the same number. Okay? So if A is a vector and K is a scalar, where K is included in a set of real numbers, then Ka is also a vector, and we are performing scalar multiplication. So if K is greater than 0, Ka and A have the same direction, here. If K is less than 0, Ka and A have opposite directions, shown here, where A is going diagonally to the, where A is going northeast, and here, where you're multiplying by minus 3, and it's going southwest. So if K is equal to 0, Ka is equal to 0, and it's the 0 vector. Here. So if K is any scalar, and the vector V is equal to V1, V2, then Kv is equal to Kv1, Kv2, as I explained earlier. Vectors between 2 points. So say you have the vector OA going there, and OB going there. And you want to try and find the length between A and B. So AB, which is what you use to describe this vector, it is equal to AO. So you're going from A to O, and then going from O to B, and so you will be transcribing that area, but you'll be going about it a different way than just simply going across. You'll just be going down the kind of the shape's sides. And it's important to note that this vector here is going upwards, but we'll be going down it. So it will be minus OA. Whereas this, because we're going up the same direction that the arrow is pointing, will be add OB. So the distance between AB will be minus OA add OB. So we'll then we'll then use subtraction. So then it can also be rearranged to put OB minus OA. So B1, B2 minus A1, A2. So the position vector of B relative to A is AB is equal to OB minus OA, B1 minus A1, B2 minus A2. Okay? So parallelism. So say we put the vector A, the vector 2A, and the vector 1/3 A. They're all parallel vectors, but they've got different length, so they're not equal to each other. So two non-zero vectors are parallel if and only if one is a scalar multiple of the other. So given any non-zero vector A and non-zero scalar K, the vector Ka is parallel to A. So each of these have some kind of factor of A in them. It's just that they've been multiplied by different things. So here it's multiplied by 1, multiplied by 2, and multiplied by 3. So they do have different lengths, but they've still got the same they have different magnitudes, but they've got the same direction. Apologies. So if A is parallel to B, there exists a scalar K such that A is equal to KB. So if A is equal to KB for some scalar K, then A is parallel to B, and the length of A is equal to the modulus of K, so all K values are positive, times the length of B. So the length of A is equal to something times B, and that something has to be positive. Then A is B, but it has some factor of A in it. Right, so unit vectors. So given a non-zero vector A, its magnitude length A is a scalar quantity. If we multiply A by the scalar length A, we obtain the parallel vector 1 length of A with length 1. So a unit vector in the direction of A is 1A, A. A vector of length K in the same direction is K, A. And a vector of length K, which is parallel to A, could be add or minus K, A. So with the length of 1, you put 1 up there, and with any length, you put K up there. And if it's just parallel to it, and it could be either going up or down, could be either going in the same direction or other direction, it's add or minus. Okay? So determining line equations. So suppose a line passes through a fixed point A with position vector A, and that the line is parallel to the vector B. So according to this diagram, so consider a point R on the line so that OR is equal to R. So by vector addition, OR is equal to OA. Remember, we're going up that way, so it's positive. And then AR, and this is going up and down, so it's just positive anyway. And C here, we've got an A, so we can just replace OA with A. So, and this here is called R. So R is equal to A add AR. So since AR is parallel to B, the line B, AR is equal to TB for some scalar. T is included in the set of real numbers. Remember, T can also be K. So R is thus A add KB, TB. Because B is parallel to AR, thus it must be multiplied by a scalar to get AR. Okay? And this is just continued. So we've seen that in Cartesian geometry, that we can determine the equation of a line using its direction and any fixed point on the line. We can do the same using vectors, so suppose a line passes through a fixed point A, A1, A2 with position vector A, and that the line is parallel to the vector B, B1, B2. So if Rxy with position vector R is any point on the line, then remember the previous slide here? Then R is equal to A add TV, where T is included in the set of real numbers, or XY, or the component form XY is equal to A1, A2, add the scalar T times the vector B1, B2. And that is the vector equation of the line. And the gradient of the line is B2 over B1. And you can see it represented here. So since xy is equal to a1 add b1 times t, a2 add b2 times t, the parametric equations of the line are x is equal to a1 add b1t, and y is equal to a2 add b2 times t, where t is included in R is the parameter. So t, or k, or whatever you would like to call it, it is the parameter. So each point on the line corresponds exactly to one value of t. And we can convert these equations into Cartesian form by equating t values. So using t, so we rearrange these formulae. So t is equal to x minus a1 all divided by b1, and it is also equal to y minus a2 all over b2. We can obtain b2x minus b1y is equal to b2a1 minus b2a2, and that is the Cartesian equation of the line. So remember vector equality, where you have to have the same magnitude and length, where it's only translations. Currently we will be on non-equality of the vector equation of a line. So consider the line passing through 5, 4 and 7, 3. When writing the equation of the line, we could use either point to give the position vector A. Similarly, we could use the position direction vector 2, minus 1, but we could also use minus 2, 1, or any non-zero scalar multiple of these vectors, because remember, here you will be going across 2 on the you will either be going across 2 here, you'll be going across 2 here, and then down 1, or you'll be going don't worry about it, across 2 here and down 1. So we can thus write the equation of the line as x 5 4 add t 2 minus 1, where t is included in the set of real numbers, or x is equal to 7 over 3 add s minus 2 1. So you can either go from 5 4 down here, or you can go from that way to that way. So where s is included in R, and so on. So we use different parameters t and s when we write these equations, and it's because the parameters are definitely not the same. So when t is equal to 0, we have the point 5 4, but when s is equal to 0, we have the point 7 3. And this is because when we're using the the parameter t here, we're starting at 5 4, but when we're using s, we're starting at the point 7 3, and we'll get different kind of direction vectors. So the parameters are thus related by s is equal to 1 minus t.